I left yesterday. So, so if I don't know if you remember, but this was the term that was dominant in the eddy momentum in the eddy fluxes, and so it comes from the correlation of the thickness and the pressure or Montgomery stream function, sorry, Montgomery potential gradient, and which has obviously a part like that. And then it has these two terms that are the correlation of the eddy perturbation of a height of a buoyancy surface correlated with the eddy perturbation of the Montgomery potential gradient, and then this other term. And really what I want here to do is just make the connection between these terms that we've actually seen before in the quasi-geostrophic TEM, where they take this form. So instead of d by dB, you have d by dz, and then you have f naught, the Coriolis parameter, v prime over b times b prime over n squared. So this term b prime over n squared is for small fluctuations of the buoyancy surfaces equal to these displacements. Okay, and you can show that quite easily by just placing yourself at a constant buoyancy place. So this is a constant. And then if you have a mean stratification associated with n squared, remember you have to do that in QG. And then there's a small perturbation. Now, if this is a constant, then you can expand in Taylor series this term, and you get that the small displacement is related to the minus the perturbation in buoyancy divided by the mean stratification. So that's that term. And then if you assume, as you do in quasi-geostrophy, that your velocity is in geostrophic balance, then this term here becomes f naught v prime. And now this is clearly related to this term. And what this term, which is the principal one, that in that diagnostic turned out to be the larger terms of all the Eliason palm flux, does is it takes the momentum put in at the surface by the wind and transfers it vertically across isopycnals. Okay, so this is how you transfer momentum from the surface to the bottom, where it's eventually not dissipated but transferred to the earth. Okay. So it is through this term here, it's form stress, which happens whenever you have that the pressure surfaces and the buoyancy surfaces are out of phase. Okay. Yes.
Paola, can you remind us what m is in the equations?
M is the Montgomery potential, so it's the equivalent of the pressure and buoyancy coordinates. Okay, so so the expression of m in terms of zeta. Let me get this right. So let me open the other presentation. I'm sorry. Nope. Sorry, can't read. Okay, I have to open the other file. Blah de blah de blah. Here it is. So where is? Hopefully, I've written it down. TWA. Yes, there it is. So if zeta is this is valid even without the bar. This is valid in general. So zeta is the displacement of the isopycnal, and here is the Montgomery potential. So you see, this is the hydrostatic equation. So it's very, very similar to where here you would have B normally, and here you have the dP dz. So it's the equivalent of the pressure. Yeah.
Going back to that.
Here.
No, the figure, yeah, the second side of this one.
Yeah.
What is the things that are going in and coming out of the board?
Oh. I think these are, say, Westy. So this is like velocities. This is V, little v's. V going into the board and coming out of the board.
And that's just geostrophic balance with the pressure force?
Approximately, yes. That's right. Yes. Okay. So now, so the thickness weighted average equations can be written in any coordinates you want, and although they are derived in buoyancy coordinates, they can be rewritten in this case, for example, Cartesian coordinates, and then in that case you have the pressure and the vertical velocity instead of the Montgomery potential and the diapycnal velocities. And so there is a velocity defined like that in 3 dimensions. And so you can try and use these equations instead of the normal Eulerian equation in Cartesian coordinates to solve directly for the residual or thickness weighted average flow in principle. So, but in practice, this has been done, so far as I know, only once, and so far. And then the problem is what do you do with these terms that are averages of eddy fluxes? So they need to be parameterized. And as we've seen, the dominant component of those EP fluxes is this form stress. Here it is. And the proposal by these gentlemen here at Los Alamos, which is actually an idea that is rather older, proposed by Rines and Young in 1982, is to parameterize them as vertical viscosity of horizontal momentum. Remember, these go into the momentum equation. And so, because they perform the same role as the form stress, which is to transfer momentum vertically. Okay, that's what they do. And so, physically, this is what a vertical viscosity also does. Okay. Now, so that's how this parametrization is implemented. And I just want to remark that in principle, you can remember that what's in the equation is the divergence of the E minus P EP fluxes, and these form stress terms are then you have to take the vertical derivative of that, right? So then this will look, once you take the vertical derivative of that, this will really look like vertical viscosity with possibly a non-constant coefficient of momentum diffusion. So this is how they appear, right, in the equation. And so you can think of them as an added velocity in the Coriolis term, okay, which would look like that. Now, if you parameterize them as in terms of the vertical shear of horizontal velocity, and you further assume that these velocities are in geostrophic balance, then these Coriolis terms, or these velocities that sort of appear in the equation, look like the vertical derivative of the slope of the isopycnal. Okay, it's because grad rho over d rho dz is the slope of the isopycnal, in fact minus the slope of the isopycnal. And so but then this coefficient here is, and with a coefficient here, which is related to this viscosity here through this relationship. So the coefficient, this kappa A, is the coefficient of viscosity here, mu, times n square over f square, which is non-dimensional, right? So it has the same dimension. And I talk about this because this parametrization will come, is also being used, and we'll talk about that in a moment. So anyways, so these gentlemen coded this up, these equations, with this vertical viscosity parametrization. Yes.
I forgot what mu and sigma bar.
Okay, sigma is the thickness, is the inverse of the buoyancy frequency, if you will. Okay. And then mu is just a coefficient with dimension of meter square per second that you have to pick as a parameter, but it has the dimension of viscosity, meter square per second. So okay, so they so these gentlemen coded it up and ran the model and compared it with the results obtained using the normal Eulerian formulation with no Eliason palm fluxes in the momentum equations, but with a buoyancy equation and a continuity equation that has these additional velocities that, oh, there they are, these additional velocity that I was just talking about, related to the vertical derivative of the isopycnal slopes with a coefficient kappa equal to this coefficient mu times n square over f square. Okay, this is, in my view, a system which is not as easily justified, but they did this because everybody in oceanography who parameterize eddies does that. Okay, this is how, and I will talk about how that is done, but for the moment, just let me say that they, so in fact they call this the conventional model. So they yes.
Can you, I mean, do they show that the system conserves energy or?
Yes, yes, because these, all you do is you just change the velocities, okay? And so in the tracer equation and in the incompressibility equation, in fact there are sort of two incompressibility equations, because these, it's not just the sum of the velocity that satisfies the incompressibility equation is each velocity separately, so the u bars and the u stars that satisfy incompressibility. And so since what is advecting the tracer or the buoyancy and all other traces, if you have more, is the combination of this velocity, which is incompressible, when you form the energy equation and integrate over the whole volume. And since this velocity also satisfies the no-flow boundary condition, then it conserves energy. Yeah.
Since there's no star terms in the momentum
That's
equation,
correct.
does
That's
this mean
right.
that the eddies don't feed back on the mean, or?
No, they do, because buoyancy is not a passive tracer, right?
Oh,
The
okay.
buoyancy changes the pressure, and the pressure
Oh, okay.
changes the momentum. But when you do, so this is a good point. So when you write the equations in the Eulerian framework, and you take an average, in the momentum equation, what appears are the Reynolds stresses, right? And in the buoyancy equation, what appears is the eddy buoyancy fluxes, right? And so this parameterization only parameterizes the buoyancy fluxes and not the momentum fluxes. So I will talk about this later in more detail, but that is the fundamental difference between the two treatments. That here you have to parameterize, you would have to parameterize the buoyancy fluxes, and if you have other traces, of course the tracer fluxes, separately from the momentum fluxes, the Reynolds stresses. Whereas in this formulation here, everything is lumped into the Elias and Pound fluxes in one big term. And in principle, I mean, you don't have to parameterize separately every little term inside the Elias and Pound fluxes, but just the divergence of the Elias and Pound fluxes. So you could say, just let me finish the sentence, that these authors say that they parameterize this, they justify, if you will, this parameterization of the Elias and Pound fluxes by observing that this is the dominant term, and we know that that the role of that term is to transfer momentum vertically, which is the same as vertical viscosity. But in reality, they substitute that for the Elias and Pound fluxes, and so that's a parameterization of the whole Elias and Pound fluxes. Okay. Yes.
So it looks like the parameterization will kill fronts of buoyancy, the diffusive parameterization. And then does it apply to scale much larger than a Rossby radius? Or
Oh yes, of course. Okay, so yes, it does not kill, but relax fronts. That's exactly what it does. And yes, it does apply on scales much larger than the deformation radius, because that's exactly the point about solving these equations when you do not resolve the Rossby deformation radius, and therefore you do not have explicitly baroclinic instability, and you have to parameterize. Of course, there's many scales that you parameterize, but the motivation for making this choice is to have exactly the if you let me go on, this will maybe be clearer later. So anyway, these people at Los Alamos, they coded this up in a numerical model of the ACC forced by surface wind, surface buoyancy, in a channel, I believe, and they compared the results of this formulation using the residual, the thickness weighted average formulation, and of course what you have then as a result, which is in dashed lines. These are, so the dashed lines is the zonally averaged zonal velocity, thickness weighted of course, as a function of latitude and height. The colors is the overturning stream function, so associated with the zonally average meridional velocity. Of course, always thickness weighted, because that's all you got here. And the solid lines is the zonally average buoyancy. Okay, again, as a function of latitude and longitude. And so this is using thickness weighted average. This is using the Eulerian mean with these fluxes parameterized as I discussed. And then since you have to compare it with the residual or thickness weighted velocity, that's what they plot for u and v. Okay, so it's the sum of the Eulerian velocity that is comes out as an output of the model together with these parameterized velocities associated with the slope of the isopycnals. And they didn't plot the difference, but it's very small, the difference. And so these two formulations agree because of the flow is nearly dystrophic, and because of all these Elias and Palm fluxes terms, the only one that really matters is that form stress. And for that, there is this one-to-one connection in the two cases. If momentum fluxes or Reynolds stresses were important, which they don't seem to be here, at least not vastly, then they wouldn't agree. So the summary so far is that the residual mean formalism or thickness weighted average formalism is very useful to capture the effect of eddy fluxes on buoyancy transport. And if you are interested in knowing the transport of buoyancy or potential temperature or other entropy-like quantities, that is what you have to look at, not the Eulerian mean flow, because that is deceiving. It's deceiving both in the atmosphere and the ocean.
I have two questions. The first one, did they compare their results to the eddy resolving simulation that they also had? Because eventually that's what you care about, or I missed something here. They're comparing
No,
two different
because it's a different calculation. They don't have topography. It's not the same
because
setup.
I think it's Ferrari, Marshall, and then Wallis after that have written exactly the same equation and simulated the channel in that formulation with the vertical friction, and they were finding that the result wasn't as compelling as one might hope, because the eddy resolving simulation was forming jets and momentum fluxes did matter.
Okay, well that may be, but the what Marshall and others did was not this. They did not. I don't believe they had exactly this, because did they solve the same exact equation? But yes, but their U, those, yeah, but there's a difference though. What they solved, like Marshall and Ferreira, I think, was this with the U being the Eulerian. And so then when they wanted to, yes.
It's the, well, they call it the residual because they just parameterize everything in the momentum budget, so it becomes the residual velocity.
Oh, so it's then it's exactly the same.
I mean, their formal discussion left a lot to be desired, and now it's clear where it comes from.
Right.
But in practice, the equation they solved were
So
the same.
and yeah, I didn't go back and reread that paper honestly, and so I don't remember it very well. But so you're saying that their result was that actually there was discrepancy because they had momentum fluxes. Well, there you go. So that's a good point. I mean, but it's interesting though that in the diagnostic of of Todd Ringler's paper that I showed yesterday, the momentum flux were really small. Maybe because their domain is so short, it's possible. They only had 1,000 kilometer in the east-west direction. I wonder if that is too short to allow jet formation, or maybe. Well, 5 kilometers is good enough. I'm trying to think of other simulations at that resolution, whether they did get jets. Yeah, exactly. I'm trying to think. I think to be honest, I mean, the computations that Christopher Wolf did and Ryan did with me, for example, were, well, I think Ryan's were even at less than 5 kilometers, and we never got really jets. So I don't know what the problem is. Maybe it's the forcing is too large scale. Maybe the forcing, we always pick these idealized winds that have a very large scale, and maybe that's what the problem is. Maybe you need winds with smaller north-south scale. Anyway, let's press on. Okay. So anyways, so this, I think this is pretty clear from this discussion that this is an issue, right? How to parameterize the momentum fluxes. Maybe, are you going to talk about that a little bit in your last lecture on jets? Well, anyway, there are some ideas, but they haven't been implemented yet. Yes, Antoine?
I have just one short question about the simulation of the Antarctic circumpolar current. It's about the role of topography or not, and related to bottom friction.
Yes.
So is it in that case you need to have a high bottom friction to?
Probably. Yeah, I think so. If you don't, so I think what Antoine is alluding to is the fact that if you have a flat bottom at the bottom of the AC Antarctic circumpolar current region, then the only way to get rid of the momentum that you put at the top with the wind, and you then transfer through form stress and then percolates to the bottom, is through bottom friction. And if the bottom friction is not very large, then you get this humongous depth-independent east-west velocities. Instead, if you have some topographic ridge, you can transfer that momentum to the Earth much more effectively, again through form stress at the bottom, but form stress instead of against buoyancy surface, against the actual topography, by having pressure differences on the two sides of the ridge and pushing the Earth that way. And so yes, so if you have a flat bottom, you must put a big bottom friction, or live with a very big zonal velocity, which apparently doesn't make any difference at all to the meridional velocity. So the two things seem, although the mechanism of course are similar, they seem to be pretty decoupled. So it doesn't really matter very much if you get 1,000 Sverdups instead of 170 to the meridional overturning, if that's what you care. If you care about the transport, of course, you're off by whatever. All right, so it's pretty clear that climate models do not resolve eddies, and so this is an old, but I think very useful comparison that Bob Holberg at GFDL did of the difference in the velocity. This is the speed in color, is the speed, surface speed of an ocean model. Okay, that stopped already. Oops. If you have a 1/6 degree resolution versus 1 degree resolution, and aside from the fact that obviously you don't see all this detail, there's also the problem that the mean currents are weaker. And so it's not just that you don't capture all these details, which is quite obvious, but really even if you coarse grain this or average, the numbers are different and the patterns are different. So this is a problem. And for climate models, you need to do simulations that are rather long, and so that is difficult to do at higher resolution. So for decades, the issue of parameterizing eddies has been discussed and studied. And in oceanography, there was a piece of work by Gent and McWilliams that was rather influential, is still, I think, very influential. In fact, is the most cited paper in the journal that it was published, JPO. And so the idea is to sort of have a general approach to the diffuse flux of a tracer. And let me just say that at the outset, these authors did not address the issue of how to parameterize Reynolds stresses. They just abandoned that issue and just focused on parameterizing the eddy fluxes of tracers. So here you have your general equation of conservation of a traces, which for a tracer phi, which is conserved except for diffusive processes, which in the ocean, once you're below the mixed layer, are very small. Maybe they become large at the bottom again, but Raf will talk about that. So now, if we're interested in large scales and long times, which I'll call the mean, then of course you have the divergence of these eddy fluxes. And you can try and see what these eddy fluxes, how they behave by looking at the variance equation. So you form the equation for the perturbation, for the eddy phi prime, and then you multiply by phi prime on average, and this is the balance. And the source term for the perturbation is this. Okay, if this is 0, well, when you look at the equation for the phi prime, which wouldn't have this term, right? If this term is not there, then there's no fluctuations really. So to get a hold of what these fluxes do, you have to look at what balances this source term for fluctuations. So these are just transport terms. They're important, but of course, when you average everywhere, they go away. And so one approach is to just say, well, the source of variance here is balanced by the dissipation of variance, which is a negative definite operator. So this term, which what we're after, v prime phi prime, times the gradient of the mean tracer is negative. So we can write this as v prime phi prime minus kappa, where kappa is positive times grad phi. And if you will, this is a definition of kappa. But the important thing is the sign, and that is that this is negative, or that if the diffusion is the diffusivity is not small and this dissipation of tracer is large, then you expect the flux to be down the mean gradient. But if diffusion is weak, then you expect this term to be approximately 0. And in that case, what that says is that the eddy fluxes should be not down the mean gradient, but orthogonal to the mean gradient. So how do we do that? So then you generalized, if you will, this equation which here had a constant, by putting in front of it a tensor whose sign is not definite. And that tensor can have a symmetric part in general, and an antisymmetric part. And the symmetric part, which you can always sort of diagonalize in this way, is guaranteed to have that property here that is down the mean gradient. Whereas this antisymmetric part, which you see has nothing the diagonal, and in general, really you only need two terms, because at the end of the day, all you want is the divergence of this guy. Okay, you're not interested in the full vector, but just its divergence. Then in this case, when you form, when you look at A times grad phi, that will turn out to be orthogonal to grad phi by construction. And so it satisfies this property that the fluxes, instead of being down the mean gradient, which is this part, will be orthogonal to the mean gradient. I think I'm going to skip this.
Question.
Yes.
In the variance equation, why the other terms are not important here?
No, they are locally, but you agree that if the velocity is incompressible, when you average over the whole domain, they will go away, right? So even though it's true that locally they will change the dynamics, they have to average to 0. And so when you, so that's, no, you're right. There are important locally, no doubt. But in some sense, they can't determine the sign, the general sign of this, because they have to be a little bit positive and a little bit negative in order to average out to 0, right? And so this term for sure is important. I mean, this term in principle too, right, if you're not in statistical steady state. So these are sort of, you know, hand-waving arguments, and but they do lead to, I think, interesting conclusions that in general you can always write this as that, and when this is not even sign definite, as this isn't, then that's sort of the most general form, and maybe you don't like this justification, but this is where it you mean because it's diagonal? I didn't. Oh yes. So I think Oliver is asking why only the diagonal terms are here and not the off-diagonal terms. And again, you can fill this matrix with other symmetric terms, but at the end of the day, you only need the divergence. So it will be the other ones are kind of doing nothing. I actually think there's only two that are important. You can even omit a third one, because the number of degrees of freedom that you really have after you take the divergence is limited.
You said that you can eliminate the other two off antisymmetric terms in the matrix A, but those wouldn't they represent an overturning horizontal circulation?
Yeah, I think again those are related to the rotational component of the velocity associated with that, which goes away when you take. I've done the algebra. Even if you add the third term, which would be like these guys, right? And when you take the divergence, they drop out. Or there's only a combination. There's only a combination of two elements that matters in 3 dimensions. So there's a gauge. I mean, for the vector, it makes a difference. But because what enters the equation here is the divergence, then they only enter in certain combinations, and you only need to really have two independent ones. And actually, I think I added this, but I think it's the same for the diffusive one, that there are really only two that are independent, not 3. We can do the
super fast. What are D bar, and D prime again? Sorry. Big D.
Oh, the big D. Okay, this one.
On the right.
Oh. Yeah. So okay, because so in principle, your diffusion is not a constant, right? It could depend, diffusivity, it could depend on time and space. And so depending on what your average is, which in general is both time and space, there could be a fluctuating component. So I should call diffusivity, yeah, I suppose. So I think I'm gonna skip this. We can talk about it, but this is just examples of how you. Let me just I'm not gonna go through it, but let me just say that you can do passive scalar examples, picking a given velocity field and see how and calculate explicitly these fluxes and see what type of flows give rise to only symmetric components or symmetric and antisymmetric component. And also these simple examples show that the tensor, the diffusion tensor, is a property of the flow only and not of the tracer. Okay, even though of course you have correlations with the tracer, at least in the passive case you can show it's a property of the flow only and not of the tracer. So back to oceanography. So then the breakthrough of this paper, which is actually terrible to read, I do not recommend it. This instead is a very good and clear paper that explains it in terms of this antisymmetric tensor, which I think is much, much clearer. Nevertheless, everybody cites it. I think the 95% of the people who cite it actually don't read it because it's very difficult. Huh? Right. So the breakthrough was exactly to do this, to say, well, what are we trying to parameterize here? We're trying to parameterize baroclinic eddies. And baroclinic eddies in the interior of the ocean, which is so adiabatic, are themselves adiabatic. So they should not be like down gradient diffusion, which instead reduces the variance of the tracer. They should have this adiabatic property. So the way to parameterize them is to parameterize through this antisymmetric tensor. So I think this is, was revolution is a big word, but was a breakthrough. And then, okay, so if you use these antisymmetric components, these components of an antisymmetric tensor, then you're guaranteed that they are adiabatic. Then, if you want to mimic baroclinic instability, you should also make sure that this this antisymmetric diffusion, which is really like an advection, acts to reduce available potential energy, or as Antoine was explaining before, relax fronts or relax the slope of the isopickle. And so to do that, you just have to make sure that these components of the antisymmetric tensor are proportional to the slope of the isopickles with a positive coefficient. And this implies that the horizontal flux will look like down gradient horizontal diffusion, but the vertical flux will look like anti-diffusion, right? So we're used to, like Fickian type law, where the fluxes is down the mean gradient. Here's the horizontal flux down the mean horizontal gradient. But here for the vertical flux, here is the vertical gradient, and this coefficient is up, right? Because it's positive definite, because this is positive and this is positive. So, and in fact, so it's down gradient in the horizontal, but up gradient in the vertical. In fact, the net resultant is neither up gradient nor down gradient because it's along the isopycnals. But what this does is it tends to relax slopes. So for example, here you have two isopycnals, okay, and here the slope is positive, so V will be positive. Here the slope, well, you're on the other side, and so if you look at W, the slope of this is positive, but wait a second, in the center here, D rho, I'm so close I can't really see it. So let's see, d rho dz, well, is always positive. So you have a vertical velocity here and a meridional velocity in this direction. So what you try to do is just pull this up and push it out. And so this big slope here will tend to be flattened because this is pulled up and this is pulled away, and so it flattens the surface. And you can show that indeed this formulation reduces the available potential energy like baroclinic instability does. Okay, and you can show that when you have a tensor, an antisymmetric tensor applied to a tracer diffusion, that is equivalent to a velocity advecting the tracer whose component have this form. And it's not difficult to prove. It's just like 2 lines of algebra. So in this Gentile-McWilliam case, the associate velocities are in this form. The horizontal velocity is proportional to the vertical derivative of the horizontal slope, that's a vector, and the vertical velocity is proportional to the horizontal divergence of this slope vector. And so you can think about it, and that's what was being done in, that numerical calculation here. This velocity here that was put in the tracer equation was exactly that. Okay, and that's how it comes about. Now you wonder, why are you spending all this time talking about this parametrization? And it's because it's really helpful to use in theories of the deep and abyssal circulation. And so without that, it's kind of... And so the great success of this parametrization is that when applied to general circulation models, so what were they doing before, you might ask? And what they were doing before, they were parameterizing the eddies with just horizontal diffusion, without that vertical component that is anti-diffusion. And so what that was really doing, since your isopycnals are typically not horizontal, was actually adding a lot of cross-isopycnal diffusion and making the model very, very sluggish. And above all, they had this problem of this cell that was doing very strange thing. This is the Deacon cell. Again, this is the zonally average meridional overturning in the Eulerian. Well, that's all there was. That was transporting heat the wrong way, and it was a real disaster. And when they added the GM parametrization, the circulation was less sluggish. The Deacon cell changed sign, and everything was much better. And so Peter Gent, who's a British gentleman, invented this, sort of wrote this limerick, and the model that they was using had the acronym MOM, and NCOM started for NCAR, so it's an acronym of an acronym, NCAR CCM ocean model. And so there it is. There once was an ocean model called MOM that occasionally used to bomb, but eddy advection and much less convection turned it into a stable NCOM. So they were quite happy about this, and this is why really that paper is cited so much, because it's very successful. Well, that may be, but certainly not with the horizontal diffusion. So okay, so the main message I think to take away is that is to go to an antisymmetric diffusion tensor, making it proportional to the isopycnal slope, so that the net result is restratification of the fluid, which mimics the decrease in available potential energy by equilibrated baroclinic eddies. Of course, you still have the problem of this coefficient, which is certainly not constant, possibly not even positive everywhere, point by point. And there's tons of papers written about this, and I didn't summarize them because I just think that the field is just not converged. So I wouldn't really know how to draw a conclusion. Well, as I said, this is an issue. But the reason why I went into some detail about it is because it's very helpful to use this parametrization in idealized and conceptual theoretical model of the abyssal circulation, which is what we're going to talk for the next, I forget what time we stop, 10:30, the next 30 minutes. All right, so first of all, you've seen these Raf showed some of these sections yesterday. So he
Paola,
showed. Yes.
before you begin, about this parametrization.
Yes.
So nowadays they are used in the model that are not eddy resolving.
Correct.
Still, but they are no more used in the eddy resolving model.
Well, the truth is that even in eddy resolving models, you can use them instead of horizontal diffusivity with a much smaller coefficient, and they're numerically very well behaved. So they stabilize the numerical schemes without adding too much diffusion or reducing the variance. And so even in eddy resolving model, it's beneficial to use this type of form, but with a much smaller coefficient, much smaller, orders of magnitude smaller.
So it's a naive question, but if, as you describe it, one way would be to have a long isopycnal diffusion and across the isopycnal diffusion.
Correct, with vastly different coefficients.
With vastly different coefficients.
That's exactly what is done.
Yeah.
But the difference is like 8 orders of magnitude in between the diapycnal and isopycnal. So typical values in the isopycnal for non-eddy resolving models is hundreds to 1,000, whereas the diapycnal one is 10 to the minus 5. So there's 8 orders of magnitude difference.
So basically, it seems to be useful to parameterize either eddy at the scales of the Rossby deformation radius,
or smaller when you don't
or
resolve them.
sub-mesoscale.
Correct. That's
eddies.
exactly right.
So basically, the justification from the processes is not really the point here. It's more an a posteriori justification, but it works.
Well, I don't think so. I think the motivation was because okay, let me put it that way. Any parametrization which is antisymmetric will not change the variance, right? But the fact that it's proportional to the slope is what makes it look like baroclinic instability. So that part, I think, is conceptual and not just that it works. Then the fact that numerically it works so well made it a great success. Because you can have a brilliant idea, and then when you implement it, it's terrible. And so it doesn't catch, right? So, yeah. But that's a good point. I mean, and you're right. It is used also to parameterize submesosphere because it works so well. We used it, and it was very beneficial. So,
sorry.
Yeah.
Sorry. Just another question before you begin.
Yes.
Because so in the first figure you showed in the beginning of this part, you said that the currents will intensify when you had these eddies.
Yes, that movie.
Yeah, that movie, right?
Yeah.
So this is the surface. These are the no.
Yes, it's surface speed.
Surface speed. So a simple question that I have would be, the forcing is the same, right? It's the wind.
Yes.
So where does the momentum go in the case where you don't have eddies? So why do the current intensify when you have? I mean,
the momentum in the vertical or in the horizontal?
So I mean, I mean you are giving the same amount of energy to the ocean in the two cases.
Yes.
And in one case you get more surface speed than in the other. So
yes,
somehow
yes. Okay, and so the reason is why. Yeah. Okay, and the reason why that is because in addition to having to parameterize the eddies, when you have coarser resolution models, you need to also put larger viscosity, and that is inescapable. And the reason why that is because of these damn boundary currents. Okay, because their width at the end of the day depends on the explicit viscosity. And if you don't resolve that width, your model bombs. Okay, so you see here there is a current that is much thinner than this, and that's because the viscosity in this model is undoubtedly much smaller. So you put the same amount of energy at the top, but you extract more through friction.
Since you're specifying the wind stress and the rate of work, which is the rate of wind work would be the stress times the velocity, it's not clear that you're putting in the same energy in the two cases.
That's true. That is true.
The one with the bigger velocities probably has larger energy supply.
Possibly.
Yeah.
Possibly. Although, since what matters is the correlation of the wind with the surface velocity, I'm not sure.
Right. But it's a general issue, I think, when people take it for granted that the energy input is somehow specified or known in advance.
That's true.
And in this example and in all others in oceanography, we don't actually know the rate of work of the wind because it's always F dot U or tau dot U, and we need U.
That's true. It's a very good point. Thank you. Right. That's it. I mean, it's not clear that the correlation is the same, but I suspect that it's probably more. So what is shown here is a form of potential density. I won't go into details how that is defined. This is the Atlantic, and this is the Pacific, and there are different colors because the contour distance, the distance between contours changes as you go down. It decreases. Otherwise, this would be all homogeneous. But no, there are gradients. And now the main thing that we need to understand is, why is there stratification in the abyss? We put all the gradients in density, buoyancy at the surface, and yet you see gradients at the bottom. How did they get pushed down? This is the question in oceanography. Now, in the upper ocean, we understand how they're pushed down. There's the wind, which converges. which creates Ekman currents that converge, and in certain places like the subtropics really mechanically pushes it down. But it does so up to about 300, 400 meters, no more. So the question is, why isn't the abyss filled with the densest water all the way up to the thermocline? Would we call this the main thermocline? That's where the wind pushes it down, or that's really is the question. So you have to, because that is a situation actually of lower potential energy, and so something that when you push less dense water down, some kinetic energy must have been expended to raise that center of mass. So where does it come from? So as the talk before explained, the energy comes from the winds and the tides. But how does it really get into the abyss or even the deep parts, which we call sort of mid-depth region? Now, one thing that it's really quite striking when you look at these pictures is that the slopes in this region, which is the region of the Southern Ocean, which is approximately circumpolar, is much steeper than everywhere else. Okay, and so especially in the Pacific, once you leave that circumpolar region, then the isopycnals or buoyancy surfaces are pretty much level. Yeah, they wiggle up and down a little, but not that much. Okay, and that's also true in the Atlantic, although then they have some slope up here, which it's not in the Pacific, because in the Pacific we don't have a mid-depth overturning circulation. And so, in fact, the current theories really show that the stratification of the world ocean is essentially set in the circumpolar region of the Southern Ocean and sort of transmitted to the global ocean from there. So the first thing to do is to understand how the stratification in the ACC alone, the Antarctic circumpolar region, is formed. And to do that, you look at the buoyancy balance in the Antarctic circumpolar region. There it is. Okay, and for the moment I'm neglecting horizontal diffusion, because it's not really important, except very close to the boundaries. And then for the moment, let's be interested in the zonal and time average properties. So you zonally and time average, that's what the bar means. And of course you have the eddies here to deal with. And I'm going to take kappa v to be a constant, and so there's no bar in kappa v because it's a constant. So now in the we conceptualize the ACC as a periodic region, periodic in x, periodic in longitude. Okay, and so because it is periodic in longitude, in the interior, the zonally average pressure gradient in the x direction is 0, and so there is no geostrophic meridional velocity. However, there is an ageostrophic velocity in the top Ekman layer, whose transport, so here V bar indicates the velocity, where capital V indicates the vertically integrated velocity, so that's the transport, is just proportional to the wind stress, zonally average, but I'm going to assume that it's only a function of latitude, so the wind is, the full wind is equivalent to zonal average. And that's the expression of the Ekman transport. That's only true in the top Ekman layer. And now if you assume that there's, well, regardless of whether there's topography or not, in the bottom, whether it's an Ekman layer or a topographic region, you have to have that the same flow is returned, right? Conservation of mass. What goes north has to come south. And that can only occur at the bottom, because in the middle you can't have any meridional velocity. But you do have a vertical velocity that is, the vertical velocity that is pumped in or out of the top Ekman layer, right? That's the Ekman velocity, which depends only on y. And it's, here I've drawn the stream function associated with this v bar equals 0 and w equal w Ekman. This is the expression for the Ekman velocity. And that's only a function of y. So this is a calculation where in a periodic domain in both x and y. And so the wind stress is westerlies, or towards the east here, and easterlies towards the west there. But in the Earth's ACC, the winds are westerly. So you should just look at this part. I should have maybe masked that part. But anyway, so that's what the overturning stream function look. That is an idealization of the Deacon cell. There it is. Okay, for a flat bottom. Now, I haven't talked about buoyancy yet, but this is the southern hemisphere, so you're going from cold to warm, and typically the ocean is stably stratified and it's warm at the top and cold at the bottom. And so a circulation like this would tend to overturn the temperature.
So, Paola, I have a very simple question. Can you explain what makes why the circulation sign change at about 2,000 kilometers?
Because the sign of the wind stress changes.
Yes.
I should have drawn the wind stress. This wind stress is positive here, goes through 0 here, and it's negative there. So there's a sign change, and here's where it's 0.
So it's related to the atmosphere jet?
No. This is just, I should have just masked this because it's confusing. This is just a calculation where it was periodic in y as well as x, and so the wind stress was both positive and negative. But in the Earth's ACC, this part does not exist. So I don't know. Can I just, maybe I'll mask it now. I don't know. Okay, mistake learned. Just don't forget about this part. Don't look at it. Sorry. I should have put a big black box on it. Okay, so again, here's the buoyancy balance, and let's assume for the moment that we neglect these eddies. We just do not put them at all. Let's assume that they are 0. And so this is a calculation where there's a ridge here in this channel. So this is a calculation where there's a channel that ends here, and then from here on there's a basin which stops. So it's just this is just the region you have to look at, and there's a topography in the form of a blade that right at the channel that stops the flow. So the wind is all towards the east, and in the channel, which is this region south of this dashed line, then you apply some surface buoyancy prescription as well. You see that the buoyancy surface, which is what is plotted here, they're vertical until they turn under the topography. So the topography doesn't occupy the whole bottom, it's just a blade. Okay. And so if you don't put any eddies, this is what they look. They are completely vertical. Now, if you allow for eddies, here explicitly resolved, then these isopicals, instead of being vertical, they slump. And the stratification is beginning to look like the one we observe in the ocean, at least the zonally averaged one. So if you put the eddies and you assume that they are adiabatic, then they have to be orthogonal to the gradient of the buoyancy, and you can define a stream function of this form, v prime b prime over b bar z, and rewrite this equation like this. Okay, this is just a rewrite of this original equation using this definition of an eddy stream function. Yes?
If the eddies are always transporting b prime orthogonal to the gradients, how do the buoyancy surfaces slump?
Because there are because their strength is proportional to the slope. So well, let me show you. Okay, we're going to do that problem right now. Okay. So if the eddies are if the eddy fluxes are orthogonal to the gradient, then you can rewrite these pieces as being as the advection of the mean buoyancy by a stream function of this form.
Excuse me?
Yes.
Could you define the term adiabatic eddies?
So adiabatic means okay, yes. Okay. So that means that they are not subject. Can I erase this? They're not subject to diabatic effects. So if you have that your original equation is, this is now in 3-dimension, equal to 0, you can write the mean equation. Well, it's written there, so I won't rewrite it. And then you have the eddy equation, which will have terms like u prime dot grad b bar plus u bar dot grad b prime. And then there'll be u prime dot grad b prime minus u prime dot grad b prime bar, right? To 0. And now, well, maybe I should just, let me just, since this is incompressible flow, no, I want to leave this like that. U prime dot grad b bar and so forth. So again, this term here and this term here, these are transport terms. And so we always think that, they don't do very much. They just rearrange stuff. And so the main source term is this. And now when you multiply this equation by b prime and average, you find d by dt of b prime square average, and then you have plus u prime b prime dot grad b bar plus u bar dot grad b prime square on 2 bar. And here I have plus u prime dot grad b prime square bar. And so again, these are considered sort of things that just are moving stuff around. And so if this right-hand side is 0, then you think that, So these are adiabatic eddies, right? There's no diabatic term here. And now the further assumption is that the dominant term in this variance equation is this. And it is so large compared to the other that it has to be 0. And so the fluxes are orthogonal to the gradient. And this, you see that, okay, one point. The reason why I wrote this before writing the variance equation is that fluctuations in B prime occur because there are fluctuations in U. So this is the source term for fluctuations. Okay, if this term weren't here, you could just set B prime equal to 0 happily, and the equation would be satisfied. But this, because there are U prime terms, then you cannot have B prime equal to 0. So that is the most important term. So there's no rigorous way to say that when eddies are adiabatic, then this term has to be 0, because there's all these other terms. But let's just say that if this term is 0, then the eddies must be adiabatic.
So, can you describe the difference from the point of view of the energy cycle between the two situations?
Well, here there's no eddies, so all the energy is in the mean, and here there's some. So you want to know how much the partition between the mean and the eddies?
I mean, I guess the wind drive the system.
Yes.
You also have buoyancy effect, and then you may have exchange between kinetic energy and available potential energy.
Or potential energy, yes. So usually the way this works is that the wind drives a component of the velocity which is sort of independent of depth, and that part is just taken up by friction and is kind of not available. But then there's a component of the wind work that is sort of available for the motion, and that drives both the mean and the eddies. Of course, it drives the eddies not directly because the wind is steady. So the wind work is only forcing directly the steady. It's only steady. It's a steady component, right? But then, I mean, I think the way to think about this is imagine that you suppress the eddies by, for example, directly solving the zonally averaged equation without this. Right? So not having any x dependence. Okay, this is what you would get. Well, in the channel anyway, not in the basin. That would be a bit of a problem. But in the channel. So, and this exactly is what you would get. Right, these vertical buoyancy surfaces. You know, you could write a zonally symmetric model. You could actually almost solve it analytically. And then allow x dependence, and this is your basic state will have some u here, which will have a shear associated with a vertical shear associated with this meridional temperature gradient, which is very large actually, because this is sort of maximum available potential energy and still be stably stratified, right? And so eddies will start growing, and they will remove the available potential energy, and you know, so the kinetic energy that is gone into the eddies is being taken away from a state, from this available potential energy, and I suppose they're not super efficient, so they're not. Don't make them completely horizontal, but they take up quite a bit of the available potential energy and settled into this equilibrium, which is sort of intermediate between flat and what you had before. Now, if you want to know the actual numbers, one has to do the calculation, the diagnostics. More what?
I don't know if it's the same question than Freddy, but could you show us with like simple arguments, like Parcell's arguments, why the situation on the left is kind of the maximum of available potential energy? Like, how can you release kinetic energy, and why is it the most efficient way of doing so?
Well, okay. So you agree that if my isopicals were tilted this way, it would actually be unstable, convectively unstable, because that's just not allowed. So the next best scenario, which is not unstable but has the maximum available potential energy, is when they're vertical. No, you can't. I mean, we can try and do it later in the discussion section, but when the standard sort of discrete case of one or two types of density is when they are sort of separated by a vertical partition, and they just they are vertical. I mean, do you agree that this is less AP than this? So what more AP you could have here is when they are unstably stratified, but that is really beyond the...
Couldn't you play on the horizontal density gradient?
Ah, that's fixed by the boundary condition at the top. Ah, that was your question. So the buoyancy is specified at the top. Yeah. Okay. So now we can rewrite this in this way, and now let's assume that there is no diffusion. So this is equal to 0. So what this says is that the advection by the mean is completely compensated by the advection by the eddy fluxes. And the solution of this equation in general is that the sum of these two, which is the residual circulation that we've been talking about for the past 2 hours, is a function of the mean buoyancy. So in other words, that the residual flow has to occur, not just the eddy flow, but the residual flow has to occur along isopicals. Now that can't be true everywhere, right? Because there is a surface here that you can't go through, because that's the surface of the ocean. So there has to be eventually some crossing of the isopical, which we assume happens near the surface in the mixed layer. So when we say this is an adiabatic theory, it's not true that it's adiabatic everywhere. It's only adiabatic in the interior, and then here it's not. Right. So we have 2 problems here, and I'm about to wrap up. Before we can solve this equation, we need, first of all, to determine what this functional relationship is. And secondly, remember that, this stream function is v prime b prime over b bar z. So what we're after is b bar. And it will be eventually an equation for b bar, but we have to relate v prime b prime bar to the mean buoyancy. And that's where it's useful to use this parametrization Gender-McWilliams, so that residual stream function is proportional to this ratio, which is also the slope of the isopical. And now, if we specify this, we can solve the equation. So, in general, and we will see later in the lecture that how to determine that functional relationship between the residual stream function and the buoyancy. But for the moment, as an example, let me just show you what happens if you assume that there is no residual circulation. There's complete compensation between the meridional mean overturning and the eddy overturning. And so we set that to 0. And then we use, so we know that was given by the wind. And now we've specified, we've parameterized rather, the eddy fluxes in this form. And since this is the slope, already you've solved a huge part of the problem. The slope is given by the ratio of tau, the wind stress, the density, which you know, F, which you know, and the eddy coefficient, which you don't know, but you would have to specify in any model. So that's the first result without doing almost nothing, right? We just, well, nothing. Assuming that there's complete compensation between the meridional mean overturning and the eddy fluxes, and using Gentile-Macmillan's parametrization, from doing no work at all, you'll already find that the slope is a competition between the wind and the eddies, if here just expressed as this eddy coefficient. So let me stop here.
Thank you.
Yeah.
Could you comment on how does this sloping by the Gent-McWilliams scheme help to change the deep water formation? Because I feel like when you have the vertical isenpic, then there's the whole area is going to be convecting, right? And there's a lot of deep water formation everywhere in the high latitudes. Now, when you have this slanted isenpics, I feel like they're not going to really easy to sink down to. Is that right?
No, it will still sink down, but it will sink along these slumped isopicals. Now we're going to talk about that. I mean, this is, for the moment, we're just, for now, the only thing that we have done, assuming that there is no residual circulation, is that, and I haven't quite finished, but the rest is very easy. We can even do it maybe in the discussion session, I don't know. We've determined the stratification in the Antarctic circumpolar region. That's big progress, right? Because I've shown you that once you've done that, that pretty much sets the stratification in the rest of the world ocean. So before, we didn't really have stratification. Let me show you here. You see there is actually no stratification here, 0. Okay, there's a front in the middle, which depends precisely on where the details of the topographic feature. That's a bit worrisome. But here, no stratification and no stratification. Okay, here instead, there is stratification up to about 2,000 meters. So, because these are the same exact isopicals, so here there was just none, right? So here there is stratification. So we have actually determined the stratification of the ACC in the ACC region, and as I will show you next, it's that propagates into the rest of the world. Yeah.
So far we have been talking about the effects of wind on ACC. I'm wondering whether it is important to consider the ice processes. Yeah.
Of course it is. But at the end of the day, as far as this problem is concerned, what the ice processes do, and I'm sure Raf will talk about it, is to provide some buoyancy flux here at the poleward edge of the ACCs. That's, as far as the ocean goes, the ice will regulate the buoyancy flux by reducing it, essentially insulating, and providing instead some freshwater flux. So, but that's a good question, because as I go forward, you will see that it's quite easy to solve for the stratification when you have specified buoyancy condition at the surface. And you can then consider this adiabatic limit, which is quite easy. Or easy, it has some advantages. Whereas, and I hope we can I can at least allude to that, when you instead have buoyancy flux condition that are specified, which is the appropriate boundary condition when you have ice covering, then the problem becomes very difficult. First of all, because it is compulsory to consider diffusion and the diabatic limit. Not fully adiabatic, but the full diabatic problem. And it's much harder.
Paola, I have a naive question because I never thought of that before, but here you get the slope as a function of kappa A, so it is in the framework of the parametrization
Correct.
that is used in the model. So, but if we want to think of these slopes independently of this parametrization,
so we can just put it in.
Is the slope related to something like marginal stability with respect to baroclinic?
No. The baroclinic instability, the baroclinic. Okay, let me first of all answer your question. So I just have to look at my notes. So here we have that psi star is equal to, no, I need the previous one, sorry, V prime B prime bar over B bar Z. That's the exact result. And then psi bar, how do you call it, bar? Bar, yes, is minus tau over rho naught F. So if that is equal to minus psi star, that's equal to V prime B prime over B bar Z. So if you want, you can say the stratification B bar Z is equal to minus V prime B prime bar, and then, the tau over rho naught F. I hope I got the algebra right. So I no zero here. So if you don't want to make any assumption except diabatic eddies, which is already, a little bit iffy, this is a general result. Okay, it doesn't tell you anything about the slope, but it tells you about B bar Z, and if you knew the Z dependence on this, then you have to worry about the boundary condition at the top. You can, if you have all the information about this, that's a general result.
Right, but is it correct that the dynamical process beyond fixing V prime, B prime, and maybe also BZ bar is the baroclinic instability?
So that's your question. Okay, sorry, I forgot about the second part of the question. Yes. So, yes, it is baroclinic instability, but it's fully equilibrated baroclinic instability. I will, I should actually show you a movie of what it looks like,
and
at
so
least in a model.
In some cases,
nothing to do with the final equilibrated state, has nothing to do with the linear stability. That's on a different scale, and nothing.
In some cases, when there are some timescale separation, then it's adjusted state such that it is marginally stable or unstable with respect to baroclinic instability. It will not be the case here.
No, this is forced baroclinic instability. You have the wind that is constantly replenishing the energy, and the final equilibrated state, I will dig it out and show it tomorrow, so or later, whatever. I have it on the laptop. Just to show you a movie of the initial onset of baroclinic instability and then the final equilibrated state, they look nothing like they are completely different.
Okay, so I think we will stop now. Thanks again, Paola.